All right, thank you very much. Also for the invitation to talk to you today. Well, it took me quite a while. Well, we from the TU Wien and from also where my second affiliation is the DWH Simulation Services company. We are working together with the Austrian government for quite a while. So I think almost since February, using modeling and simulation for decision support of their coronavirus strategy. And well, I have like hours to talk about. There are so many interesting things, and Scholdan told me, okay, just tell something about your work, and okay, I could have done something technical, some technical introduction to what our model looks like, but probably to some of you this would not be so interesting. Probably some of you could not even follow because it's quite mathematical. So I decided, okay, I go one step higher. I do not only tell what we are doing in particular, but in general, what is to be done with respect to modeling and simulation of the spread of the coronavirus, and in particular, well, what is the secret behind those models? What is modeling and simulation in general? And what's the secret behind those epidemiological models? And then finally also, well, how reliable are they? So what is the uncertainty? And well, if some model believes, okay, that there is a forecast of that many infectious persons, what does this mean and how reliable is that? So I figured out, okay, this is just a quick overview of what I'm going to tell you. And yeah, probably some of you learn something, and it helps you to interpret the things you are reading on the media. Like if you're reading of a new model of a university of somewhere, then you get at least some kind of an idea what is behind this model and what's the idea behind that. Okay. Let's go into that with what is modeling and simulation in general, and why do we need that in particular at this point. I'm sure some of you are working in the artificial intelligence area, some of you are working in the data science area, and in my experience, in particular, those kind of people have a lot of difficulties to understanding the idea of modeling and simulation. So I will give a quick overview. So the idea is always, well, we have a certain question we want to answer. Okay, I give it on a very low level at the first step, and I promise it's getting more interesting. Okay, so how do we get from a question to the answer? And the scientifically original way was doing, okay, I'm doing some experiments. Okay, I've got a question, I want my answer, so I'm trying it out. So if I make some repetitions of this thing, if I want to know how fast my apple drops from the tree, I need to make some experiments on how often it drops. Okay, when I have done more and more experiments, and I have figured out some laws, I have figured out some systematics in behind, I will be able to establish a theory out of that. So like Newton's gravitational law, okay, I know the apple drops with a certain acceleration, and I can use this theory from that point on as a supplement for the experiments. If the setting is similar enough, then I can use the theory to answer my question. And the problem is, or that's where modeling and simulation comes into this circle, or into this process. If I'm not able to do the experiment, and if I'm not able to have, or if I don't have a theory for something, then I need something in between. Then I need something that is something like an experiment, but not really an experiment, because I'm not doing it in real life, I'm doing it in a computer. And it's also not directly theory, because it's not just coupling a few equations or so, but rather something more complex, a complex dynamical system which I need to evaluate, which I need to simulate in order to get some sort of an answer. So that's the basic strategy of modeling and simulation. It's some third pillar between experiment and theory. Okay, this is now very abstract. I would like to give a very, well, some brief example of how this process could work in reality. It is not coronavirus, it is on purpose something completely different, but we will get to COVID-19 very soon. Okay, let's say we have a paper plane and we want to figure out whether a paper plane flies further than 5 meters or not. That's a very specific question, and of course we need to do something in order to answer it. Well, we can make some experiments. We can fly the paper plane a couple of times, and we will find out in most of the cases it flies far further than 5 meters. And I can give in this case, okay, I cannot give a yes or no answer, but probably you can give something like a statistical answer, and you can say, okay, in 80% of the cases, the paper plane was flying further than 5 meters. Okay, now you change the paper plane. You increase probably the wingspan of the paper plane. Okay, you again perform some experiments, and you find out that in 70% of all cases now it was further than 5 meters, and you're happy with that. Okay, now you have done a couple of experiments, you have done some observations, and you can somehow establish a general paper plane theory. Like you can establish, okay, if I have a paper plane that is somehow this arrow type, then I know that my probability of the paper plane flying further than 5 meters is something that depends somehow on the wingspan or something like that. And you have something like a theory which you can use further on for all of the paper planes with the type of the arrow. Okay, now for this arrow, okay, the wingspan is smaller, so according to your established theory, the probability of it flying further would be higher. Okay, and now you're in a completely different situation. Now you're in a situation where you have a completely different paper plane like this one. You cannot use your general theory about paper planes because, well, it's not an arrow type paper plane, so it is not directly applicable. You cannot do experiments because, let's say, this is your only sheet of paper, and you don't want to risk that it breaks or something like that, or that it gets lost or something. So you only have one chance, but you need to know, and that's the place where modeling and simulation comes onto the board. Okay, I somehow derive or establish a mathematical paper plane model. I use all my findings that I already have. I use the findings from my general paper plane theory. I use my data from all my experiments, and I couple those two things with additional knowledge about physical laws, with a causal knowledge I know about air resistance, about movement of air, and so on, and with all the things I already know. And I couple all the things together in a big paper plane model, here represented by some Bernoulli equation. Does not really matter where this comes from, but that's the idea. And now I have a mathematical paper plane model, and okay, I simulate this model, I make some simulations, and it turns out, okay, according to this paper plane model, okay, this paper plane does not fly very well. This is somewhat plausible because to all of you who have already tried out making a paper plane like this, you will already know that this is not very successful. Okay, now you have a simulated result, and you have some idea of when the paper plane does fly further than 5 meters or not. But, and that's the big problem with all of that, you did not make an experiment with that. You did not use your perfectly founded and validated theory. You used something in the middle. And with something in the middle, you have a high uncertainty. You have a so-called model uncertainty. Because, well, your previous knowledge could not be used directly. You have probably a simplified model because you did not include, I don't know, the air pressure. You did not include like small rips in the paper and so on. So a model, and in particular a mathematical model, is always a simplification of reality. It's in your computer. It's not the reality. It's something in your computer. So there are some things which you cannot depict, and that altogether makes a certain model uncertainty, which you always have to take under account. So every result that comes out of your simulation is to be considered with respect to all the model uncertainties. And you need to know all the uncertainties when you want to use your model result for something. Okay, now I've talked a lot about paper planes. Let's come to something more interesting. So like something why you're all here. Let's say we have also a very specific question. How is, for example, the coronavirus going to spread in Austria? What consequences will it bring for the population? What kind of things can be done to interfere with that? That's a very specific question. Well, it's not very specific, but it's specific enough. And we have been asking ourselves this question like at the beginning of February, when all this became present, and when the first coronavirus cases appeared in Austria. And well, of course, we had to do something with that. We need to answer this question. And we have basically the same problem with the paper plane. this is a completely new situation. We have something completely new which has never been present. The virus is new. Nobody knows how it's going to evolve, how it's going to spread. We cannot make experiments. Of course, we cannot. That's ethically not possible because, well, you cannot just infect a certain amount of people just to look how it spreads. It's not possible. There are, if you want to interpret it this way, unintentional experiments from countries who have had the virus before Austria, in particular. Of course, you can use the data which is known from other countries, but and that's what we learned very fast, that countries are not comparable on that level. We cannot compare Italy with Austria. Have a totally different social behavior, have a totally different contact behavior. You can also not compare China with Austria. You cannot compare Spain with Austria. You cannot, well, particularly actually you cannot compare any two countries, because at least the healthcare system in the two countries are usually different. But nevertheless, that's some information, but it's not all the information we need. On the other hand, okay, in Austria, we have a very well-founded theory about how virus is spreading in Austria, in particular with respect to the influenza virus, which is, well, it's very regular in Austria. It appears every year, and it comes at a certain time and it leaves at a certain time. So we have a very well knowledge about the wave of the influenza virus. And you do not need to be a modeler, you do not need to be a mathematician in order to tell when the virus is going to occur in Austria, because the healthcare experts know. You can ask any virologist in Austria and he will tell you perfectly, okay, when is the influenza epidemics occurring this year, probably. There is a lot of things is known about this virus, but the new virus is different. So we have a different transmission rate, we have a different dispersion factor, and so on. So a lot of things are different with respect to this new virus, and that's the situation. That's why we need something in the middle. We need some simulation model that basically tells us, that basically takes all the information we got, that takes all the information from all the data, from all the experience of other countries, that needs to include all the information that is known from infectious spread in Austria, of all the other infectious diseases, of the healthcare system, and so on. And of course, additional causal knowledge about this system and how this works. So that's actually the idea of how modeling and simulation is done, and why it is necessary. Because, well, we neither of the two things, neither the knowledge about influenza nor the data from other countries is sufficient to give answers on how the virus is going to spread in the new environment. Well, of course, there's a lot of things with respect to model uncertainty. I will come to that later on at the end of my talk. But there are a lot of model uncertainties that needs to be taken into account in this case. But before I come to that, I'm going to tell you a little bit about what kind of models are there used. Here, this is just some example, but there are a lot of epidemiological models that are used currently. And I'm going to tell you a little bit on how they work. I'm going to tell this with respect to model structure and with respect to model classification. And when we are talking about epidemiological models, we have a very top-level classification, which basically decides on, okay, whether you're using a solely data-based model or you're using a causal model. Both of these things have been used quite a lot in the recent times for some kind of forecasting ideas. And this is, so to say, the top-level classification of these kind of models. When we're using a database model, we have a lot of data. We have basically no causal information, but we are combining a lot of different data and using a certain method in order to extrapolate this data somehow. This can be done by a learning method, by machine learning, by supervised, unsupervised learning, by some statistical extrapolation method, and so on. So there are a lot of different things. It has a lot of advantages because it's very transparent. It is, well, most of the cases is very transparent. You can fit the current numbers almost perfectly, and you can find a very feasible trend of how it's going to continue. But then that's the interesting thing about epidemics. In most of the cases, this is not enough. Because when we are talking about fitting some numbers, when you put yourself into the situation of a few months ago, then we had a very sharp exponential increase of the disease numbers. And of course, if you're using some kind of statistical methods to fit this trend, then of course you would get something exponentially. And talking about the exponential growth is very okay. At the beginning of the epidemics, when everything starts to spread, we have an exponential increase. We have these reproduction factors, we have these doubling rates and so on. But when you continue with the exponential idea, okay, now probably in 1 week I have 10,000 infected. In 2 weeks I will have 40,000 infected. In 3 weeks and so on. When you continue this idea, then you will reach a point where the number of infected people is increasing the population of your country. And that's the point where your extrapolation becomes implausible, because an exponential extrapolation can never ever predict some kind of an epidemic peak, what you see on the right-hand side picture. It's impossible to detect this peak by solely a database method. And that's why it is so important to use causal models for epidemic forecasting, or for epidemic decision support, so to say, or for epidemic models. So database models are fine, but in most of the cases, you will need some causal models in order to get a broader view of the whole situation. What's the idea behind that? Okay, you're taking also data, but the data is not the focus. The focus is actually the logic that occurs in your system. So this is basically the idea. While a database model is always based on the data, you put the data into a certain method and you get a solution. While a causal model is usually tackled from the causalities that occur within your system. We have infected people, we have susceptible people, the infected people infect the susceptible people, and so on. All this is the knowledge, the causal knowledge about your system. And then finally, at the second stage, you include the data, you include the parameterization data, and find a solution to the problem. So that's a completely different focus, and well, not a focus, but a starting point. So that's the idea behind causal models in contrast to database models. Okay, now with respect to causal models, also here you can distinguish between a couple of different strategies. Probably the most famous strategy was founded in 1927 by Kermit and McKendrick, and it is by far the most simplistic strategy, but also still the most elegant solution to the whole problem. The idea are so-called macroscopic or aggregated model, where you consider the population split into certain compartments. You say that the population itself is whatever is in your compartments stuck together, and each compartment denotes a certain subpopulation. In the classic SIR model, which is short for susceptible, infectious, resistant, or recovered, however you want to say, you have 3 compartments in which you distinguish your population. You say that there is a big compartment, usually at the beginning, in which all your susceptible persons are. You have one compartment which is small at the beginning of your epidemic, where you have infectious persons, so the people which are infectious by contact with susceptible people cause more infections. And finally, you have a certain compartment with resistant persons, like if you recover from your virus, either if you die or if you survive and get enough antibodies, then you fall into the third compartment, which is basically the resistant or recovered persons. And the strategy, so the secret behind this model is that, of course, you have a certain sequence in which these compartments are run through. You have the susceptible compartment where people come from and usually get into the infectious compartment. From the infectious compartment, you get into the resistant compartment. So that's the standard flow in your model. And the secret actually behind this model lies into how fast the things flow into the other compartments. Of course, in the recoveries, so the resistance, we have a certain recovery rate. So recoveries per day, you can somehow imagine that as the more people are into the compartment, so the more liquid is filled into this tank, the faster it flows out. This is somehow the relation. You can imagine it in your head, and it's actually a linear relation. For the first flow, it's not so easy because actually, of course, it's the same idea. The more susceptible people, the more flows into the infectious compartment. But this flow from the susceptible to the infectious also depends on the infectious. So that's a so-called nonlinearity in mathematics, where both compartments actually influence that. But don't care about these details. The basic image about this model is this flow structure from one compartment to the other. And of course, there are different ideas, or there are different strategies how you could compute that. You could say, okay, per second, a certain of people are running from there to there, from there to there. So you update this in model in seconds. So you make a so-called difference equation out of it. You could also consider this as a so-called differential equation and solve it with a differential equation solver. That's the classic strategy. So there are different ways on how you update your time in this model, so to say. Okay, that's the most simplistic model, and of course, since 1927, a lot has happened that extends this idea. The most basic or the most important extension for the spread of the COVID-19 is to include a fourth compartment at least. And this compartment is very crucial. It's the so-called exposed compartment that comes between susceptible and infectious. Like when you become susceptible, when you become infected by an infectious person, and you start to develop your disease, you are not instantaneously infectious. You are incubating, so to say. You are within your latency period. You are not yet infectious. You do not feel any symptoms. The virus is growing in your body. And this takes a couple of days. In case for the COVID-19, it's expected to be about 5.1 days, or and until you develop symptoms, and at least 3 days until you are potentially infectious. So you have some time period in which you are neither susceptible nor infectious, and that's the exposed compartment that comes in between. And though it looks very similar, this system now, it has some kind of a delayed behavior. It's a very interesting thing from a mathematical point of view, and there is a big system change between the classic SIR strategy and the SEIR strategy. So this is one very important model extension that makes a big difference, in particular for the current coronavirus, which has a comparably long latency time. But of course, you must not stop there. There are a lot of possible extensions to that. You could implement a whole patient pathway, so to say. You could, for example, say, okay, you start with some quarantine compartment, you start with some hospitalized compartment. You could also split compartments into age groups, for example. Then you could distribute, then you could observe, for example, everything age dependent if you want. So like you can say, okay, I take the susceptible not as one compartment, but the susceptible from 0 to 10, from 10 to 20, from 20 to 30, and so on. So you could, you could blow up the whole system as much as you want. But, and that's also one thing which is very important for modeling and simulation. When you increase the model complexity, it does not automatically mean that your model gets more precise or even better. Because when you increase the complexity, you increase also the number of model parameters, you increase the things you need to adapt in your model, and the things you need to fit for your simulations, and therefore it must not always mean that it's getting better if you increase the number of compartments or increase the complexity. But nevertheless, this is possible, and this is done. And when you, for example, read of an SIRX model, for example, that means that you are including such kind of a quarantined compartment at the end. You have also probably heard of an SIRS model, which basically means that persons are coming back from the resistant into the susceptible, so they lose their resistance after a certain time, and so on. So a lot of these things is included into these abbreviations, and well, just to give you an idea of what's underneath these abbreviations. Okay, as mentioned, this is only one of the, so to say, two classic strategies of modeling an epidemic. The second one is much more recent, so to say. While in the macroscopic way, we took the population as one big compartment and said, okay, that the population within the compartment, well, you do not care about about the individual people. In the microscopic modeling strategy, you care about that. You say, okay, each, so to say, submodel, each element of your model is one person that has one of these states. So what has been a compartment before now becomes a state of a certain individual. And now the whole microscopic thing evolves over time. You have certain infectious person. When they have contact with the susceptible persons, they are able to infect the susceptible persons. After a certain time, the infectious persons become resistant, and so on. So that's the idea about the microscopic models. Of course, this is the much more recent strategy, because you necessarily need a very good computer to be able to compute that. Because when you think of each individual as one person in reality, then you will need a couple of them simulated simultaneously, and that requires a couple of computer resources. So this is the more recent modeling strategy, so to say. Yet I would not say that this is necessarily the better. That's the next thing. Each of these strategies, whether you're using the SIR, SEIR, the microscopic agent-based strategy, and so on, you cannot say that either of the one is the best. They're each specified for several purposes. For example, a macroscopic model or even a database model might be optimal for very short-term prognosis, while you would probably require a microscopic model for evaluation of policies and so on. So you cannot answer every research question with the same model. It depends on your research question. And that's the thing which I need to focus on, the modeling purpose. So a model should be used within the range of its purpose, and only within the range of its purpose. So and within the range of validity. So there is no such thing as a free lunch theorem in which you say, okay, there is one perfect model which you are always using to simulate epidemics. Okay, couple of things about our particular model, which we are using to support our government. Actually, it is an agent-based model because we have specified on the question evaluation of policies. When you, for example, want to evaluate what happens when you close all the schools in a country, then necessarily you need to include the schools in your model. And when you're thinking about an aggregated model, which consists of certain compartments, you will not have the opportunity to include schools in there, because you have no assignment of compartment into schools and so on. So this would not be possible. And therefore we decided, okay, we go on the microscopic scale. We make a so-called agent-based model. And these four modules here in the middle are basically the things that it consists of. The whole model is based on a very detailed image of the population. So we have a very fine image of each person, of each of us is actually represented in the model by a so-called statistical representative. Then we add up a so-called disease module that actually, a so-called contact module, which manages, okay, that how do people within the module, within the population get in contact with each other. Then we decide, okay, when the infection spreads, so if you have an infectious contact between a susceptible and an infectious person, how does the infection evolve in the body? So when do they start getting symptoms? When do they start being infectious at all? When will they be isolated? Where will they be isolated? And finally, we added up a so-called policy module in which we evaluated, okay, what happens if you close the schools, if you open the schools at a certain time, workplaces, what happens if you decrease the number of contacts in leisure time, and so on and so on. A couple of things you can evaluate. I just want to give a few slides so that you get an image of how actually what's behind our model and what kind of complexity it has. So that's what I just meant. Every one of you and also of us is represented here in the model, not in person, but as a statistical representative. So we draw from, so to say, the correct distributions and sample persons based on the total number of persons we really have in reality. This refers to a certain age. This also refers to a certain sex, but also this refers to a certain position. So each of us is represented here as a dot on a map, so to say. Each of us is represented in a model by a residence in form of a GPS coordinate, which is sampled according to a very smart algorithm. that helps us to create a spatial relation in there. And based on the spatial relations, the agents in our model have so-called locations. This might be households. These are also schools. These are workplaces. This is also leisure time. And within these locations, the agent have contacts. So we don't have direct agent-agent contacts, but we have agent location, agent contacts. So that's the idea. And that strategy enables us to evaluate policies like closing of schools, closing of workplaces, reducing contacts at leisure times, isolating persons in households, like general simulation of lockdown policies, and also lifting of the subsequent lockdown policies. And what is nowadays very important, also what happens when you start tracing contacts. So also this is possible with our model. And then, of course, we have a very specific module that allows us to have a very detailed image of a patient pathway, so to say. You see it in this state chart on the right-hand side. So as soon as somebody influences as an infectious person infects a non-susceptible person, the new infected person starts with this state chart on the right-hand side and has a certain period in which it is just incubating. After that, you get an event where infectious starts. Then you have some finish of incubation times where you start getting symptoms or not. Also, asymptomatic diseases are included, and so on. So we have a couple of events that allow us to also branch this patient pathway as correctly as possible, so to say. So that's basically the strategy behind our models. It is a very, very complex model that is generally based on the SIR strategy, because people are susceptible, get infectious, and then recover, but has a lot of additional features which extend that. Now, how about the model uncertainty? Not only about our model, of course, I can tell a lot about the model uncertainty of our model, but about these kind of models in general. And that's actually the most important slide and also the last slide of my talk. First of all, we need to consider, okay, our model has errors with respect to simplifications. Humans are unpredictable things. When you try to model humans, this is completely impossible. You need to include stochastics because human behavior is almost unpredictable. In particular, if you want to detect or you want to forecast the behavior of all the humans, it's basically impossible with deterministic laws. So whatever considers human, you are not able to depict in precise. So you need to consider that you have to make simplifications somewhere. And although our model is going very much into the details of human behavior, of the human daily life, still we have a very simplified version of what's really reality. What's also very important for COVID-19 is now the total amount of data errors occurring everywhere. We have a lot of data sets available for deaf persons, for hospitalized persons, for confirmed, so like positive tests and so on. We have very intelligent registers where all of this is documented, but still we have a lot of bias in there. Like what happens if you start screening somewhere? Then of course the found tests are going to increase. Reporting, you get reporting delays, you get reporting bias, because that's one thing we found out, that for example we had very few positive test results on the weekend, while surprisingly on Monday we got a lot of positive test results. So apparently on Monday people get sick very often, and so on. So there is a lot of bias in all the data sets, and in order to model that, you need to somehow be aware of the bias and be somehow able to filter it somehow. So that's also one thing that needs to be considered in uncertainty. But probably the most important part of the uncertainty is a somehow occurring feedback loop. When you are doing forecasts, when you're doing prognosis, like if you want to try to make a weather forecast, you look at the current weather, you look at the history of the weather, and you make a forecast for next week. And this will occur or not, but nevertheless, it's a system you can observe, and you will see whether it occurs or not. In case of COVID-19, this is different, because the system you want to forecast is changing not only based on the levels of the disease, not only based on the disease levels, because then if the numbers are bad, you make policies. If the numbers are good, you will release the policies. But also on the forecasts. Like if scientists say, okay, we expect millions of infectious persons, then of course the government will react on that. And of course the prognosis will not occur. And that's one thing that a lot of people are not aware of, but needs to be considered, that actually we as a modeler and simulation experts, we at the moment are not able to make prognosis that will occur. It is not possible because there's this feedback loop. When our prognoses are telling, okay, the numbers are going to evolve nicely, then we will have a lot of policies removed and so on. So then probably the situation will be different. If our prognoses are bad, then we will make policies to going into the direction of the lockdown again. So this is very, very difficult and brings us in a very uncomfortable position. And so whenever you see a prognosis, think of it rather as a scenario of what's going to happen if the current situation is continued somehow, than a real prognosis. So you cannot, please distinguish that from a weather forecast, which is going to occur or not. And with these words, I want to finish my talk